Although sources and loads are most often connected in Y, it's not uncommon to find a delta connected load, and therefore the analysis of what we call the Y delta circuit. I might not have said that earlier. You always state the source and then the load when you're describing the connection type. So YY, both are connected. Y delta means that the source is connected as a Y and the load is connected as a delta. Delta Y would obviously imply that the source is connected as a delta and the load is connected as a Y. So what's more common though, or I guess not as common as the YY, but somewhat common, is the Y delta. Load connected as a Y, sorry, source connected as a Y, load connected as a delta. If the load in a three-phase delta circuit's balanced, it can easily be converted into a Y equivalent for analysis using this, what we call the delta to Y or Y to delta transformations. Here you'll see I've introduced a new term. I'm actually not calling it Y anymore, I'm calling it star. I guess that's a more modern naming convention, I guess, of this circuit. So here what we've done is we've represented a load, RAC, RBC, RAB, that's, you know, the phase loads, RA, RB, and RC for the delta, or for the Y or the star. And then I've just provided you here with some formulas for the conversion. For unbalanced systems. For balanced circuits, the equation here is going to reduce to ZY, the impedance of the Y connected branch is just going to be equal to Z delta over 3. So for a balanced circuit analysis, there's a substantial amount of reduction that gets done, and the only equation you have to remember to convert between the two is ZY is equal to Z delta over 3. After the delta load has been replaced with its what we call its Y equivalent circuit, we can perform an analysis using the single phase equivalent that we just showed, exactly the same method. Once we've calculated the line currents in the transformed circuit, we then have to use the line currents to find the currents in each leg of the original delta load using the relationship previously defined. Okay, so now we need to do an example of doing this Y delta analysis. So although you can use KVL and KCL to perform this analysis and you'll get the correct answers, the easiest technique is to use what's called a delta to Y transformation that we just talked about. So in this, anything that's connected in the delta form, you convert over to its Y equivalency. You then replace that in the circuit and do the analysis. So you can read for yourself here what the problem statement is, and then continue. Pause while you read this, and then continue on to the analysis that we'll perform on the next slide. So, what we've got here, if we were to just draw the circuit, we've got a three-phase load, of course. That's not a three-phase load. Sorry about that. Those are our voltage sources, internal impedance of the generator, line impedance, and then the difference is that over here we've got this situation. The load's connected in a delta shape, and what we want to do is we want to, use the delta to Y transform here. I'm just say delta to Y. That's the technique, is we need to replace, we need to replace this portion with a Y equivalency circuit. So I'm going to back up for a second, and here's a comparison of the two loads. We'll
better drawn than I was able to draw it on the last one. And what you'll notice is that in a Y equivalent, if we had wires here, we have a phase voltage measured across the phase, and then we have a line voltage. So those are different. Line to line. Sometimes this voltage is called line to line. In the delta, V phase is equal to V line to line. Right? They're the same voltage. In the star, we have a line current that's equal to the phase current. The line current in the delta is not equal to the phase current. This is phase current flowing here, right there, that guy. So the analysis is a little bit different. So what you need to do is, when you do your Y equivalency diagram, you need to calculate your phase voltage. You then need to convert that to a line-to-line voltage. The line-to-line voltage that you calculate for the Y equivalent is the same as the phase and the line-to-line voltage for the delta. So you got to calculate phase voltage in the star, go to line-to-line voltage in the star, and then go to line-to-line and phase in the delta for voltages. For currents, what you need to do is you calculate just the current in the delta or in the star circuit, IC or IL and I phase, they're the same. That gives you this line current entering right here, and you can use the known relationships between I line and I phase in a delta circuit to calculate the individual phase currents. So that's the approach that we're going to demonstrate here for this guy. So now that we know what we're going to do, let's just go ahead and do the math. So the first thing we have to do is calculate our Y equivalency load. And for a balanced circuit, meaning that the impedance of all the phases are equal, we just divide the phase impedance by 3. So that was 118.5 plus J85.8. We divide that whole thing by 3. That gives us 39.5 ohms plus J28.6. And we'll write that as ohms per phase, right, to indicate that that's a balanced load. If we were to draw the equivalent, I'm going to draw the A phase, 120. The internal impedance of the generator comes next. That was 0.2 resistance and 0.5 inductance. That's the end of the generator right there. The next thing we have is the transmission line, which was 0.3 and 0.9 ohms of inductance. That's the end of the transmission line right there. Now we've got the load, which we just calculated as 39.5 resistance and 28.6 ohms of inductance. So we want to calculate the for the Y equivalent, we want to calculate IAA, which is both in the Y, that's both the line current and the phase current. So IAA is equal to I phase is equal to I line. And so that's just equal to 120 at an angle of 0. We divide that by the sum of all these impedances, 0.2 plus J.5 plus 0.3 plus J.9 plus 39.5 plus J28.6, and that gives us 2.4 at an angle of negative 36.87 degrees amps. The B phase is just this rotated by 120, so 2.4 at an angle of 83.13, and the C phase for the Y equivalent is 2.4 at an angle of 203.13. So the next thing that we're going to do is we're going to use this current flowing through here to calculate the phase voltage in the Y equivalent. So that's just IAA times ZA. So that's 2.4 at an angle of negative 36.87 degrees. We then multiply that by the load impedance ZA 39.5 plus J 28.6, and you get a phase voltage for the Y equivalency circuit of 117.04 volts at an angle of negative 0.96 degrees. Okay. So per our previous analysis, though, what we have to do is we have to convert this over to the line voltage, right? This is V phase. So we need to convert that over to a line voltage. So for a Y equivalent, the line voltage is equal to radical 3 angle 30 times V phase. So our line voltage is going to be radical 3 angle 30, multiply that by V phase, which we calculated was 117.04. If we're talking about the A phase, that's minus 0.96 degrees. That gives us 202.72 at an angle of 29.04 degrees volts. This here is the line voltage for the Y circuit and for the delta circuit. So this is VAB. That's that voltage right there. VBC is just that rotated by 120, so 202.72 angle 149.04 volts. And then VAC is that rotated by 240, which is 202.72 angle 322.72 volts. And you guys can calculate that on your own. So now we know the phase and the line voltage for the delta connected loads, just these guys here. The next thing that we needed to know was we needed to know the load currents. And on the previous current calculation, we calculated the line currents. And in a delta load, I line is equal to radical 3 angle negative 30 times the phase current. Well, what we calculated in the previous example was the phase current of the Y-connected load, which is also the line current of the Y-connected load, which is also the line current of the delta-connected load. So what we're trying to calculate now is, what we want to find is what's the phase current in the delta-connected load. So we need to do a little bit of manipulation. That's I phase is equal to I line over radical 3 angle negative 30. So just a little bit of simple algebra. So if I want to know the phase voltages, or the phase currents in the delta connected load, I just take that line current that I calculated previously, which was 2.4 amps at negative 36.87 degrees. I divide it by radical 3 at an angle of negative 30. And that gives me 1.39 amps at an angle of negative 6.87. Since I used the phase A current, or the line A current here, whatever you want to call it, this gave me IAB in the delta connected load. IBC would be that rotated by 120. IAC would be that rotated by 240. So the next part of the question was to the next part of the question was to calculate the load or the generator voltage at the terminals in both line to line and phase. I'm not going to do that because we just did it in a previous one. I'm just going to give you the answer, and the onus is on you to verify these through your own calculations. So if you want to do your phase voltage calculations at the output of the terminals of the generator, the answer that you should get is 118.9 volts at an angle of negative 0.32 degrees, and the line-to-line voltage is, you just multiply this by radical 3 angle 30, and you get 205.94 at an angle of 149.68 degrees volts. So you can verify those calculations on your own.